А, вы готовы, да? А вы? Эх, еще бы я был бы готов. Так. Okay, guys, let's start. Who slept well? Nice. Who saw the Lord of the Rings movie? Okay. Who understands the reference? Okay. The topic for today is rings. So, before this lecture, we discussed a set with one operation, and basically we dealt with groups. Now I want to switch to a set with a pair of operations. And one of the basic examples of this kind of structures is a ring. So let me give you the definition of a ring. This will be, well, there are many different types of rings. And I'm not going to give you the most general definition of a ring, but this will be the most useful definition of a ring. So, what is a ring? As usual, when you give a definition of an algebraic structure, at the first stage you should describe all the data you have, and on the second stage you should provide all the axioms. So, the part number one, so the definition. The part number one, the data. So what kind of data do we have? First of all, we have a set. This will be the set of elements of the ring. Then we have an operation, a binary operation on R. This operation is denoted by the sign plus and is called addition. And we have a second operation, which is denoted as multiplication by the dot, and it's called multiplication. So this is the data. So basically, we're given a set and a pair of operations. Currently, there is no relation between these two operations. They could be any operations. Now, the axioms. So the axioms, well, we do not want to consider just arbitrary operations on a set R. So we want these operations to be good themselves, and we want these operations to be compatible in some way. So, first of all, we want to say that addition is a good one. So there are four axioms. So we want to say that with respect to addition, the set R is an abelian group, which means the addition is associative. The second one, there must be neutral element with respect to addition. So there is 0, such that x plus 0 equals 0 plus x equals x. Every element is invertible with respect to addition. So for every element x in R, there exists element minus x, such that x plus minus x equals minus x plus x equals 0. And addition must be commutative. So x plus y equals y plus x. So these are four axioms for the addition. Now, the next axiom says that multiplication must be good enough. So let me write it down here. First of all, we want multiplication to be associative. So multiplication is and there is a neutral element with respect to multiplication. We'll denote this element by 1. There is 1 such that 1 times x equals x times 1 equals x. And then we want, as you can see here, these 4 axioms, they are about addition only. There's no multiplication here, just addition. These 2 axioms are just about multiplication. And we want to have some kind of relation between addition and multiplication, and this relation is distributivity law. So we must have something like this. And for all possible elements from the ring R. So if we are given these 7 axioms, then R is called a ring. Well, strictly speaking, the most general definition of a ring requires the first 4 axioms and the axiom number 7. This is the most general ring. When we add 5, this is called an associative ring. And when we add 6, it's called an associative ring with an identity. But I will call this structure simply as a ring. And if additionally we have the axiom number 8, which says that multiplication is commutative. This is a commutative ring. And if we add 2 more axioms, axiom number 9, which says that for every non-zero x is invertible with respect to multiplication, there is x inverse such that x times x inverse equals x inverse times x equals 1, and 0 is not equal to 1, then we will say that R is a field. So here is a ring. So basically, what I did here, I gave you 3 different definitions. When we're given axioms from 1 to 7, then R is a ring. When we're given axioms from 1 to 8, then R is a commutative ring. And when we're given axioms from 1 to 10, then R is a field. I believe you're already familiar with the definition of a field from the linear algebra course. Okay, so as usual, let's start with examples. So what kind of examples do I have? Okay, examples. Example number 1. Let's take the set of integers with addition and multiplication. This is a ring. Moreover, this is a commutative ring. Because we already know that integers with addition form an abelian group. Moreover, we know that multiplication is associative and there is a neutral element which is 1, exactly 1, the element 1. And the distributivity law also holds, and the commutativity law holds. So this is a commutative ring. Is it a field? Why? Just try your best guess. Yeah, exactly, because the axiom number 9 is not satisfied. Because if you take an element 2, there is no other integer such that 2 times this integer equals 1. So this new element must be rational, it must be 1 over 2. And 1 over 2 is not in Z. So this axiom doesn't hold here, okay? But if we switch to the rational numbers with addition and multiplication, this will be a field. So this is a commutative ring, and this is a field. Because we can divide by any non-zero element, and 0 is not equal to 1. Okay? Now, the next example, Zn with addition and multiplication modular n. This is also a ring, because, again, we already know that addition is good enough, so it's an abelian group with respect to addition. So multiplication is associative, there is neutral element with respect to multiplication, and this law also holds. And by the way, this ring is also commutative. The next question, is this a field or not? So this is a commutative ring. But is it a field? Who thinks that, what? Okay, you know, what is the best way to prove a theorem? Is voting. Let's try to vote. Who thinks that this is a field? Okay, 1, 2, 2 hands. Okay, who thinks that this is not a field? 1, 2, 3. Okay, 4. Okay, the right answer, you're both wrong. Because it could be a field, it depends on n. It could be a field and it could be not. For example, this ring is a field if and only if n is a prime number. So, number 4, if p is a prime number, then zp plus n multiplication is a field. So let's discuss why. Well, first of all, this is a commutative ring, so the axioms from 1 to 8 are satisfied, okay? It's clear that the axiom 10 is also satisfied, so we only need to check that the axiom 9 holds, okay? Who can prove that the axiom 9 holds here? Who sees how to prove this? Okay, let me explain. So, just in case, let me recall that Zp is the set of all remainders modular p. So these are elements from 0 to p minus 1. So we want to prove that all non-zero elements are invertible, okay? So we have an element A from here, and we want to prove that this element A has an inverse. What does it mean? We want to find an element B from Zp such that A times B equals 1 modular P. Okay? If we can find for any element from here an element B with this property, then it means that B is by definition the inverse element with respect to multiplication. So how to find it? Well, you see, since P is prime, then A from 1 to P minus 1 is a coprime with P. So A and P are coprime. But now, this is the usual hack. When you're given two coprime numbers, you can represent the GCD as a linear combination of these two numbers. So we can write it like B times A plus U times P equals 1. So there exist integers B and U such that this equality holds. But now let's take this equality modular P. Now when we take it modular P, well, this is 0. So we have A times B equals 1 modular P. So the remainder of B is what we are looking for. Okay, who was able to follow? Are there any questions regarding this? Okay. Is it okay? Okay, good. So, as you can see, this thing is a field if P is prime. Well, we will discuss later why this guy is not a field when this number n is not a prime. Another example, which one should I use? Okay, okay, here is another example. Let's take matrices, let's say with real coefficients. This is also with usual matrix addition and multiplication. So this is also a ring, but this is not a commutative ring, it's just a ring. Again, because we know that the matrix addition and multiplication, they satisfy the first 7 axioms. Okay, what should be next? Yeah, another example. This is kind of a stupid example. Let's take a one-point set. So in order to give a ring, I should provide you with a set and a pair of operations. Let's take the set consisting of one element only. Okay? Now, if we're given a set with one element, there is only one operation. Because here you just have only one pair, and here you just have only one element. So there is only one map from the left-hand side to the right-hand side. Okay, there is a unique operation here. And we will use this operation as an addition and as a multiplication. So this only operation will be our addition and multiplication at the same time. Now, a straightforward computation shows that the axioms from 1 to 4 are satisfied. Well, actually, in this case, all axioms, you can check that all of these are true. Well, why? Because, well, if your axiom requires to check that some equality holds, well, in this ring, every element is the only element. So if you're given two expressions, they always evaluate as this element. So every expression is equal to any other expression. So if your axiom has a form like this, something equals something, it's always true in this kind of ring, okay? Because there is only one element. The left-hand side and the right-hand side must be this only element. There is no other option, so every equality must be true. So since all these axioms, they can be formulated in terms of equalities, they're always true. The same thing happens here. You can reformulate this as a sequence of equalities, this is a sequence of equalities, this is a sequence of equalities, this is also an equality. So all these axioms are true. Well, actually, the axiom number 9 is also true, because this is the only element. This element must be 0 and this element must be 1. So this element must be 0 and this element must be 1. So for every non-zero element, there must be an inverse. But there is no non-zero elements, so this axiom also true, is also true. But the axiom number 10 is not true because 0 equals 1. So this is an example of a ring where all the 9 axioms are satisfied, but the axiom number 10 is not. So this is an example of a structure which is not a field because of the failure of this axiom. So this is an interesting example. This is what is called a trivial ring or a zero ring. And what should be next? Another example, example number 7. Let's take an arbitrary commutative ring. I want to define the set of polynomials with coefficients in A. Okay, as a set, this is the set of pictures where all the coefficients are in the ring A. This is just the set of pictures. Now, if I want to provide this set with the structure of a ring, I must define addition and multiplication. But I believe you can guess how the addition and multiplication works. You just use usual addition and multiplication of polynomials. So the rule for the addition is this, and the rule for the multiplication is this. These are just formal rules. Then the set of, this set is called the set of polynomials in one variable with coefficients in A. And then this set with these two operations becomes a commutative ring. Now, there was a subtle moment. I told you that an element of this ring is a picture of this form. Usually, probably, you heard that a polynomial is a function given by this expression. But here, I don't want to deal with a polynomial as with a function, and there is a reason why I don't want to do that. Let me demonstrate the reason. There's always a trade-off whether your marker can be visible or it can be erasable. Okay, so let's say we're given Z2 with addition and multiplication. So this is a ring. So we may consider polynomials with coefficients in Z2. Now, we have polynomials like x, x squared, and x cubed. These are distinct polynomials in this ring, because by definition, these pictures are different. So these polynomials are not the same. But each polynomial gives you a function from Z2 to Z2 by the rule. Let's say x gives you a function which takes x to x squared gives you a function which takes x to x squared, and x cubed gives you a function which takes x to x cubed. Let's compare these three functions. Well, what are the elements here? Just 0 and 1, okay? Well, each function takes 0 to 0 and 1 to 1. So all these functions are the same. So these functions are the same. So if you think about functions, there is no difference between x, x squared, and x cubed. But I want to distinguish them. So in order to distinguish them, it's not enough to think about them as a function given by this expression. So that's why I just think about them formally as just an expression. So it's not a function, it's just an expression given by this formula, okay? So there is a difference between function given by this formula and a polynomial. Polynomial is a more general thing, okay? So two polynomials are the same if and only if their coefficients are the same. But two functions could be the same even if the coefficients are different. Okay? So this is the difference between functions and polynomials. So that was probably the final example. Yeah, exactly. Now, so now we have this notion of a ring. This is our object. And as in case of a group, we had a notion of a sub-object, and we had a notion of a homomorphism between two groups. Now I want to extend these notions to the case of a ring. Okay, a subring. Well, suppose R is a ring. What is a subring? First of all, it's a subset in R. Now, what kind of properties do we have? Well, first of all, S plus in R plus must be a subgroup. Who understands what's written here? Who thinks that it requires a clarification, what's written here? Okay, and just in case, who remembers the definition of a subgroup? Is there anyone who doesn't? Okay, so let me explain what's written here. So R is a ring, so it has two binary operations. We can forget about multiplication, so then we will get an abelian group. So in case of an abelian group, we have a notion of a subgroup, so we want S with this operation to be a subgroup, well, as it's defined in case of groups. But what it means exactly, it means, well, we have to check three properties. 1a, the neutral element with respect to addition must be in S, so the zero element must be in S. 1b, the set S must be closed under addition, so if x and y are in S, then their sum must be in S. And 1c, this set S must be closed under taking the inverse element. So if an element x is in S, then its inverse must be in S. So this is property number one. So the property number two. So as you can see, this guy consists of the set, addition, and multiplication. And here we just used the set and addition. Now we want to use multiplication. We want S to be closed under multiplication. So if we have two elements from S, then x times y are also in S. And the property number three, we want the neutral element with respect to multiplication to be in S. So these are three properties we required to define a subring. So if we have a subset closed under addition, subtraction, multiplication, it has the zero element and the identity element, then it's a subring. Let me give you an example. Okay, suppose our ring is Q with addition and multiplication. This is the ring R. Let's take the subset of all integers. Then the subset of integers, it contains zero, it's closed under addition, it's closed under subtraction, it's closed under multiplication, it contains 1. So by definition, it's a subring. And by the way, when S is a subring, it has a structure of a ring. So S itself is a ring because of the property 1b and the property 2, we can restrict addition and multiplication to this subset. And with respect to this addition and multiplication, S is a ring itself. Another example is when we take the ring of matrices, then we may consider the subset of all scalar matrices. So it's here. Then the subset of scalar matrices, well, it contains 0, it contains... What again?
What are scalar matrices?
n by n.
And what are scalar?
It's lambda times the identity matrix. So it means lambda on the diagonal. This is what is called scalar matrices. Okay, so this set of matrices, well, this subset of matrices is closed under addition, subtraction, multiplication. It contains 0 and 1. So it's also a subring. So these are two examples of a subring. Well, there is actually a third example. If we take a ring of polynomials and we consider polynomials of degree 0, so not dependent on x, so just a free term. So this is also a subring. So the set of all polynomials of degree 0, they also form a subring in the ring, in this ring. Okay, so what should be next? Okay, so yeah. As you remember, when we discussed groups, we had two approaches. The approach number 1, we discussed different types of elements inside of a group. In approach number 2, we discussed different types of subgroups in a group. So somehow you can study a structure by its elements or by its subsets with some specific properties. So here we also have two different approaches. The approach number 1 is to discuss different types of elements of a ring. So what kind of elements do we have in a ring? Well, suppose we are given a ring. Then we will say that an element x is invertible in R. Well, if it's invertible with respect to multiplication, so if there exists an element x inverse such that x times x inverse equals x inverse times x equals 1. And the set of all invertible elements is denoted by R star. So nothing new. Then, the second definition. We will say that an element is a zero divisor. Well, let's say x from R, well, is a left zero divisor. If there is non-zero element y such that x times y equals 0. So it may happen in a ring that two elements are not 0, but when you multiply them, the result is 0. For example, this often happens in case of matrices or in case of Zn. And, well, you can switch the left to right here, and you will get the notion of a right zero divisor. I hope it's obvious how to formulate this, so I'm not going to write it down. So the next definition, yeah, and in case R is commutative, you just say x is a zero divisor without specifying left or right. Now, the third part, if x is an element of R such that x to the n is equal to 0, then we will say that x is nilpotent. And the definition number 4, if x is an element of R and x squared equals x, we will say that x is idempotent.
If you say x is power of n, it means with respect to multiplication.
Yep. When we use addition, we will use the additive notation like n times x, which means x plus x n times. And when we use multiplication, then x times x n times, we will denote by x to the power of n. Okay? So there are 4 different types of elements. Invertible elements, zero divisors, left and right zero divisors, then nilpotent elements and idempotent elements. Just in case, the zero divisors are denoted by dl of r. This is the set of left zero divisors. dr will be the set of right zero divisors. And d of r is just the union of the left and the right zero divisors. The set of nilpotents will be denoted by nil of r, and the set of idempotents will be denoted e of r. Okay. Now, let me write down the picture explaining how these different types of elements are related to each other. So suppose we're given this set R. Okay? Then here we have a subset of invertible elements, and this subset always contains the element 1, because the element 1 always invertible. Now, the subset of zero divisors doesn't intersect the subset of invertible elements, and it always contains 0. And the set of idempotents lays like this. This is the set of idempotents. And the set of nilpotents is here. So let me explain. So you have the set of all elements. Then the zero divisors and the invertible elements, they are disjoint. And it may happen there are some other elements which are not invertible and are not zero divisors. It may also happen that there are elements like this. Now, all nilpotents are always zero divisors, so nilpotents are inside the zero divisors, and idempotents, they may be anywhere, and they always contain 1 and 0. So this is how these elements look like. So let me give you some specific examples. Let's take z with addition and multiplication, the integers. What is the set of all invertible elements here? Plus minus 1. All other integers are not invertible, because if you take something larger than 1 or smaller than minus 1, the inverse will be a rational number, which is not integer. So this is the set of all invertible elements. What is the set of the zero divisors of z? So just 0, because there is no non-zero element such that multiplying by another non-zero element we will get 0. So that's why the zero divisors of z consist of the 0 only. Now, because of that, the set of nilpotents is also 0. Well, because nilpotents must be inside the zero divisors, and they contain 0, so there is only one option: the nilpotents coincide with the 0 set. And the idempotents of z, they are solutions of this equation, and we know that even in real numbers there are only 2 solutions, 0 and 1, so in case of integers we just have 2 solutions, 0 and 1, and these are the only idempotents of the ring Z. So, and as you can see, there are a lot of elements here between invertible and zero divisors. Like almost all the elements in Z are not invertible and are not zero divisors. So it may happen. Okay, what should next? Okay, the other examples will be I believe, during the seminar section. Okay, so let's discuss another notion. The notion of an ideal. So in case of a group, when we discussed subsets in a group, we used subgroups or normal subgroups. Well, in case, yeah, and when we discussed homomorphisms of groups, if you remember, the kernel of a homomorphism is always a normal subgroup, and the image of a homomorphism is just an arbitrary subgroup. In case of a ring, the situation is not that symmetrical. In case of a ring, well, if we want the image will be a subset which is a subring, and if we want to deal with something like a kernel, we need a new notion, which is an ideal. So the reason why I want to define another structure inside the ring, because we will need it. So the definition. Suppose R plus dot is a ring. Now I want to define a left ideal. So I is a subset of R. And what kind of axioms do we have? The axiom number 1, I with addition, must be a subgroup in R with addition. So this is very similar to what we have here. But here's the difference. The property number 2. Instead of this, we require that for every element X from I and every element R from R capital, R times X is inside I. So you can multiply anything from the subset I with anything from the ring itself, and the result must be in this subset I. In this case, and you multiply X on the left. In this case, I is called a left ideal. If you require 2 prime for every X in I and for every R in R, X times R is an I. So the element R is on the right, and then this is a right ideal. And if you want both properties to hold, so let me write it like this. If all 3 properties are satisfied, in this case, we will say that I is an ideal or double-sided ideal. Okay, in case of a commutative ring, there is no difference between left ideals and right ideals because the multiplication is commutative. And so we will deal with just ideals only, and that's it. So in case of a commutative ring, so if R is commutative, then left ideal is the same thing as the right ideal, and it's just called ideal. So there is no difference. So let me give you an example. Let's take Z to be our ring. Then, well, we already know how the set of all subgroups with respect to addition look like. We know that every subgroup, so if we take H from Z plus a subgroup, then H is of the form Z times N for some integer N, okay? And these are all possible subgroups. There are no other subgroups. So now, if we want to describe all ideals in Z, there is no difference between left and right ideals because it's commutative. So if we want to describe all possible ideals, we want to find which subgroups satisfy the property number 2. Okay? Well, if you take a look, then it's clear that every subgroup satisfies this property. Because if you are given a number which is divisible by n, and you multiply this number by anything, then the result is always also divisible by n. So every subgroup of this form satisfies the property number 2. So every subgroup of this form is actually an ideal. And there are no other subgroups, so there are no other ideals. So these are all possible ideals. Who was able to follow this explanation, just in case? Okay, good. Okay, and another example is Zn with addition and multiplication. We know that every subgroup, if H is a subgroup, then H is of the form k times Zn, where k divides n. And again, it's clear that if a remainder divisible by k, after multiplication by anything, by any other remainder, it will be divisible by k. So this is also an ideal, and this is the set of all possible ideals because there are no other subgroups. These are all possible ideals in Zn. So these are examples of ideals. Do I have any other example? Okay, so let me give you an example of a left and right ideal, just for completeness. Let's take matrices, 2 by 2 matrices with real coefficients. Now, we may take a set of matrices with the first 0 column. So the second column consists of arbitrary reals, and the first column must be 0. Well, if you multiply every matrix of this form on the left by any other matrix, the first column will remain 0. So this is a left ideal. I'm not saying that every left ideal is of this form. This is not true. But this is an example of a left ideal. And if you multiply this matrix a matrix of this form by something on the right, well, it may happen that in the result the first column is not 0. For example, if you take matrix like this and you multiply by this matrix on the right, it will swap 2 columns. So it's not a right ideal. So it's not closed on the right multiplication, but it's closed on the left multiplication. So it is not right ideal. Well, if you want an example of a right ideal which is not left ideal, you need to consider a matrix with the first row to be 0 and the second row to be arbitrary. So J with these properties is an example of a right ideal which is not left ideal. Okay. So what should be next? Okay, now I want to discuss a notion of a homomorphism. Okay, homomorphism. Well, as in case of groups, the main reason why we want to have homomorphism is because we want to compare to different objects. So if we want to compare to different groups, now we want to compare to different rings. And the most important thing, we want to say when two rings are the same. This will lead us to the notion of an isomorphism. But first, we need to define a homomorphism. So what is a homomorphism? Suppose we're given two rings, S plus dot and R plus dot. Then a homomorphism is a map from S to R. And this homomorphism, this map must satisfy three properties. The property number one, phi must preserve the addition. So phi of x plus y equals phi of x plus phi of y. The property number two, phi must preserve multiplication. And the property number three, which is not obvious one, phi must preserve the neutral element with respect to multiplication. Let me explain several details. So when we're given two rings and we forget about multiplication, then the first property says that phi is the homomorphism from one abelian group to another abelian group. So if we forget multiplication, then phi is a homomorphism from one abelian group to another abelian group. A homomorphism of abelian groups. Well, if you remember, every homomorphism of groups preserves the neutral element and the inverse element. So because of this, phi of 0 must be 0 and phi of minus x must be minus phi of x. So the fact that phi preserves 0 follows automatically from this property of a homomorphism of groups. But when phi satisfies this property, the property number 2, well, it doesn't follow from the first two properties that phi must preserve the neutral element with respect to multiplication. So we have to add this axiom additionally. So do not forget about this third axiom. So we must preserve addition, multiplication, and the neutral element with respect to multiplication. So this is important because it may happen that a map preserves these two operations, but one doesn't go to one. Okay. And if additionally phi is a bijection, and if additionally phi, so here it's homomorphism of rings. And if additionally phi is a bijection, then phi is an isomorphism of rings. And as you remember, in case of groups, isomorphism, well, the existence of an isomorphism between two groups means that these two groups are exactly the same. So it doesn't matter which group you want to study. You can switch from one group to another one, the properties are exactly the same. So in this case, if you switch from one ring to an isomorphic ring, their properties are also exactly the same. So there is no difference between isomorphic rings. So somehow isomorphic rings are the same rings. They're just presented by different constructions, which looks like they're different, but they're exactly the same. Yep.
Is neutral element with respect to multiplication unique?
Yep. It must be unique. Well, we discussed this property at the very beginning, at the first lecture. If we have an operation with two neutral elements, then the neutral element must be unique. So if you apply this statement for the multiplication of a ring, this will be it. there is at most one neutral element for every operation. And if operation is associative, then there is at most one inverse element to each element. So the inverse element with respect to multiplication is also unique, if it exists. Okay. Yeah, now I want to provide you with several examples of homomorphisms. Examples. Example number 1. Let's take z plus n multiplication and zn with addition and multiplication modular n. These are two rings, and we have a map from z to zn, which takes an element k to k modular n, which is the remainder of k with respect to n. So this map preserves addition and multiplication, and if you take 1, the remainder of 1 is also 1. So all three properties of the homomorphism are satisfied. So this is an example of a homomorphism from one ring to another one. So it was, well, when we forget multiplication, it was a homomorphism of abelian groups, but it's actually a homomorphism of rings. Now, another example. If we take the field of real numbers and the matrices, square matrices with real coefficients with addition and multiplication, then we have a map from R to matrices which takes each element lambda to the scalar matrix lambda times E, where E is the identity matrix. So this map is also a homomorphism of rings. This is another example of a homomorphism of rings. What should be next? Okay. Now, let's take polynomials with real coefficients, and let's take the complex numbers. Then, I have a map which substitutes I instead of x. Let's say f of x goes to f of I. You just substitute an element of the field C. Well, you can actually use any complex number here, or even real number, it doesn't matter which one. But if you replace x by a specific number, then the map from the set of polynomials, well, from the ring of polynomials to the field of complex numbers is a homomorphism of rings. Because this map preserves addition, multiplication, and it takes 1 to 1. So this is also an example of a homomorphism. Okay, now the Chinese remainder theorem, but for rings. Well, you know, I can see in your sleepy eyes how excited you are. You know, when you're very sleepy, usually you need sugar. Try this. And share with others. Okay. The Chinese remainder theorem. Okay. So what is the Chinese remainder theorem in case of rings? So as usual, we're given two integers, m and n, and they are coprime. Now, we have z, m, n, and now this is a ring, not just a group, but a ring. And we have zm times zn, and this is also a ring with component-wise operations. So multiplication is component-wise, addition is component-wise, the neutral element is 0, 0. With respect to addition, the neutral element with respect to multiplication is 1, 1. Now, we have a map well, the usual map which takes k to a pair of remainders, k modular m and k modular n, let's say it's phi capital, then we can say that phi is an isomorphism of rings. Okay, who thinks that the claim is obvious? Okay, who thinks that it requires some explanation? Okay, okay. So first of all, what does it mean that these guys are rings? It means that we have these two sets, and there are two operations, addition and multiplication here, and addition and multiplication here. If we forget multiplication, then we will get the usual Chinese remainder theorem that we already proven in case of groups. So by the usual Chinese remainder theorem, this map is a bijection and it preserves addition. So the only thing that we need to check in order to prove that this map is an isomorphism of rings is to check that this map preserves multiplication and the identity element. Because bijection and this property follows from the previous result. Okay? So now, but it's more or less clear by the definition that this map preserves multiplication. Well, because modular m and modular n operations preserve multiplication. And if you take 1, it goes to 1 modular m and 1 modular n, which is 1, 1, which means that it preserved the identity. So basically, that's it. That's the whole proof. Who was able to follow the proof? Are there any questions regarding the proof, or should I repeat at least something? Okay, good. So this is the Chinese remainder theorem for rings. So this is an isomorphism. By the way, if this is an isomorphism, then the set of invertible elements here corresponds to the set of invertible elements here under this isomorphism. Well, because since it's the same ring, so the invertible elements here and the invertible elements here are the same. And the same means that they correspond to each other under the isomorphism. But, well, what is the notion of an invertible element here? Is ZMN star? Well, we have two notions of star. Well, we have this star in case of Zn, and there is a star in case of a ring, which means the set of all invertible elements, but they're the same. So if we apply this star here, we will get multiplicative version of the Chinese remainder theorem. That was just a remark. I mean, so this is just a more general statement which combines two Chinese remainder theorems, a multiplicative one and the additive one. Okay. Now, the next thing. Well, suppose we have a homomorphism from one ring to another one. Well, in case of groups, we had the notion of an image and a kernel. And here we also have an image and a kernel. And the definition is exactly the same. The image of phi is the set of all elements of the form phi of x, where x goes through all elements of R. So this is just the set theoretical image. And the kernel of phi is the set of all elements of R such that phi of x equals 0. So the kernel is the set of elements here, and the image is the set of elements here. As before, the kernel lives on the left, and the image lives on the right. Now, what are the properties of these subsets? Well, in case of groups, if you remember, the image was an arbitrary subgroup and the kernel was a normal subgroup. Here, the image will be a subring and the kernel is an ideal. So the claim, if phi from R to S is a homomorphism of ring, of rings, then the image of phi in S is a subring. The second one, the kernel of phi in R is an ideal. And this is the reason why we need ideals and subrings, because the image is an example of a subring and the kernel is an example of an ideal. And this is a very important example. The third one, phi is surjective if and only if the image of phi coincides with S, and phi is injective if and only if the kernel of phi consists of the zero element only. So this claim describes the structure of the image and the kernel of an arbitrary homomorphism. Okay. There is one obvious claim here. Which one?
Second.
What again? The fourth one. I have a better option.
Second.
I have a better option. Well, you had 4 attempts, and attempt number 4 was the correct one. How lucky are you? Well, you know, so what this shows that you have to learn before going to an exam, because you have no luck at all. So you better learn. So, okay, now, this one is obvious. Why? What does it mean that phi is surjective? It means that if you take an arbitrary element from here, then you can find some element which goes to this one, okay? But what does it mean that the image of phi is S? That's exactly it. So every element here has a preimage. So this is just by definition. So there is nothing to prove, okay? Now, let's check the first one, that the image of phi is a subring. So first of all, well, since this is a homomorphism of rings, we can forget about multiplication. And this map is the homomorphism of abelian groups. Okay? But in case of groups, we already know that the image is a subgroup. So if we take image with addition, it's a subgroup. By the claim about the structure of a homomorphism of groups. Who was able to follow? Okay, good. Are there any questions at this place? Okay. Now, what else do we need to prove in order to show that the image is a subring? Well, we need to prove 3 properties. The property number 1 is this one, that the image is a subgroup in S with respect to addition. And we already have this. Now, the second property, if we have 2 elements from the image, their product must be in the image. And the third property, the neutral element with respect to multiplication must be in the image. Okay? So this is what we need to prove. But what does it mean that x and y are an image? If x and y are an image, then x is in the form phi of A and y is in the form phi of B. Then x times y is phi of A times phi of B, and since phi is a homomorphism, this is phi of A times B, but this means that the product belongs to the image. By the definition, it's represented as phi of something. And the problem number 3, it follows from the fact that phi of 1 equals 1. That was the third axiom. That was the third axiom of the homomorphism of rings. So that means that 1 can be presented as phi of something, so 1 is also in the image. So this is also true. So we have all 3 properties. So that's why the image is a subring just by definition. Who was able to follow? Okay, are there any questions? Good. Now, let's check that the kernel is an ideal. Number 2. So, again, we forget about multiplication. And so, by definition, what is the kernel of the homomorphism of groups? It's the set of all elements here going to the neutral element here, okay? But what is the neutral element here with respect to addition? It's 0. So the kernel of this homomorphism of groups is the set of elements from R going to 0. But this is exactly the definition of the kernel of the homomorphism of rings. So the kernel of the homomorphism of rings coincides with the kernel of this homomorphism of groups. But in case of groups, we know that the kernel is a subgroup here. But this group is abelian. Well, every subgroup is normal, so it doesn't matter if we mention that. But in any case, the kernel of phi with addition in R plus is a subgroup. And again, what should we check in order to show that the kernel is an ideal? First of all is this property, and we already have it. And the second property is that for every element x from the kernel of phi and every element r from R capital, R times x belongs to the kernel of phi. This is what we need. Okay, but how do you check this? Well, in order to show that something belongs to the kernel, we need to apply phi to this element, and if the result is 0, then this element is in the kernel. So let's check if phi of Rx is 0. Now, since phi is a homomorphism, this is the same as phi of R times phi of x, but since x is in the kernel, the second factor is 0, so the product must be 0. Well, I didn't prove, well, I haven't proved yet that if you multiply something by 0, then the result is 0. But let me show you why this is true. So if you have an element s and you multiply it by 0, the result will be 0. Why? Well, because 0 plus 0 equals 0. Now, multiply this by s on the left. By the distributivity law, the left-hand side is s times 0 plus s times 0, and it equals s times 0. Now you can subtract s times 0 from the left and the right-hand side, and you will get that s times 0 equals 0. So this is why the later equality holds. So this explains why this is true. So now we're done. So the kernel is indeed an ideal. Okay, now the third one was obvious. So let me prove the fourth one. Okay, but this one is also not very complicated because phi as a homomorphism of rings is injective if and only if phi is injective as a homomorphism of groups. Because it's just a property of a map. It doesn't depend on the operations. But in case of groups, we already know that a homomorphism is injective if and only if its kernel contains the neutral element only. So that's why this equivalence follows from the previous fact about kernel of a homomorphism of groups. And that's it. Okay, who was able to follow the whole proof? Are there any questions regarding the proof? Okay, and I believe that's it. Thanks for being here.